Chapter 18, Acid-Base Equilibrium. Here shows an acid dissociation reaction to generate hydronium ions. As we have seen, the acid constant is a measure of the strength of the acid, and it tells you the ability of an acid to dissociate and generate hydronium ions. Another way to look at the dissociation of acid is to calculate the percent acid dissociated, or the extent of dissociation. It is calculated by dissociated acid divided by initial acid concentration, multiplied by 100 to convert to percentage. It turns out that when the initial acid concentration decrease, when this decrease, the percent dissociation of acid increase. So in other words, compared to a concentrated acid, a dilute acid has more extent of dissociation, have a higher percentage of acid dissociated. To confirm that, we can draw a table, reaction table, and this is the initial concentration of the acid, and this is the change. And in fact, the change of the acid is the acid dissociated. So this is the dissociated acid, and this is equilibrium acid concentration. So the percent of acid dissociated must be X divided by initial concentration, times 100. So that's the percent acid dissociated. Now in the next two slides, we will do some calculations to compare a concentrated acid and a dilute acid. We'll show you that when the initial concentration decrease becomes more dilute, the X also decrease. Of course, when the initial concentration becomes smaller, you have less number of acid decrease, but the ratio actually increase. So that means the fraction of ions present increase even though the actual dissociation number decrease. In sample problem 18.9, we compare different concentration of the same acid, hypochlorous acid. The acid constant 2.9 times 10 to the minus 8. The concentration, one is 0.4 and one is 0.035. And we want to calculate the percent dissociation. To calculate the percent of dissociation, we need to first find how much acid dissociated. To do that, we need to draw the reaction table. But first, we want to write the balanced dissociation reaction. So hypochlorous acid with water forms hydronium ion plus hypochlorite. And the K is the product divided by reactant. Here shows the reaction table when the initial concentration is 0.4. So here is the initial concentration, the change, the equilibrium. To solve X, we use information Ka. We write Ka equals product divided by reactants. Here is X times X, so X squared divided by initial concentration. Now to solve this X, we realize that Ka is a very small number, and that indicates only a small amount of acid dissociate. So X should be very small, that can be negligible, and therefore this denominator is approximately to be 0.4. And that simplify the math calculation. So X should be, note that 0.4 is just the initial concentration. Okay, so if A is the acid, that's the initial concentration times this is Ka, and we have this equation: X equals square root initial concentration times Ka, and that's the equation we already showed before. Okay, for a weak acid, when the acid constant is small, and that is the hydronium concentration. Okay, that's this one. In this case, is hydronium concentration also is the dissociated acid. Okay, plug in the data. Okay, that give you how much acid dissociated. Okay, finally we can calculate the percent dissociation by the dissociated acid divided by initial concentration, give you 0.028%. Now this also justify our assumption that X is so small to omit X from this equation may leads error only 0.028, much smaller than 5. So assumption is justified. Here is the reaction table when the concentration is diluted to be 0.035. So again, initial concentration, change, equilibrium. So Ka, write Ka, which is X squared divided by concentration of acid. Assume X is too small, we can omit it. We get this equation. So again, the concentration change is initial concentration times Ka. Okay, and plug in, and that's the data. Okay, so if you compare with last slide, it's much smaller than the dissociated acid when it's the initial concentration is higher. Okay, so let's calculate dissociation percent. Okay, so this is percentage, 0.091%. Again, this justify our assumption X can be omitted in this equation. Okay, so now let's compare these two solutions. One is concentrate, one is dilute. And our calculation show the dissociation for dilute one. Okay, the dissociation is also small. So the absolute value of the molecules acid dissociate becomes smaller when the initial concentration becomes smaller. So you decrease concentration, dissociation decrease, but our calculation of percent actually increase. So this goes up. Okay, so the absolute value of molecules dissociates becomes smaller, but the percent actually increase. A polyprotic acid is an acid with more than one ionizable proton. For example, in phosphoric acid, there are 3 hydrogens to donate. So in water, it first donates 1 hydrogen to water to form hydronium ion. At the same time, it generates dihydrogen phosphate anion. Now, in the dihydrogen phosphate anion, there are still 2 hydrogens to donate, so it's still an acid. So it will react with another water molecule to generate a second hydronium ion. At the same time, it forms hydrogen phosphate anion. This molecule still have a hydrogen, and therefore it's still an acid. It can react with the third water to give you third hydronium ion and to form phosphate anion. These 3 ionization reactions has different Ka. So the first one called Ka1 is hydronium ion times dihydrogen phosphate divided by phosphoric acid. And the second one, Ka2, is hydronium ion times hydrogen phosphate. Okay, it's this one, and dihydrogen phosphate. And so you can see they all have different equation to calculate the Ka, and the values are very different So Ka1 is much greater than Ka2, which is also much greater than Ka3. Now this is not difficult to understand because initially phosphoric acid has 3 hydrogens. Okay, when it forms dihydrogen phosphate, now you only have 2 hydrogen left. Also, the dihydrogen phosphate already have a negative charge. You can see a negative charge here. To make hydrogen phosphate, which has 2 negative, you need to add another negative charge, which is make it harder. Okay, now hydrogen phosphate already have 2 negative charge. To make phosphate anion, another negative charge needs to be added, and so it makes even harder. And that's why the reaction becomes more difficult. So the K constant decrease. K1 is A1 is much greater than Ka2, Ka3, and because of that, when we calculate the hydronium ion concentration generated from this acid, we only consider the first one because it has much larger Ka1, and the second one, third one can be omitted. Here shows some polyprotic acids and their Kas. Oxalic acid, 2 hydrogen, so 2 Kas. Ka1, 10 to the minus 2. Ka2, 10 to the minus 5. So Ka1 is greater than Ka2. Sulfurous acid, 2 hydrogen, Ka1, Ka2, so Ka1 much greater than Ka2. Phosphoric acid, we already saw in the last slide. Arsenic acid, 3 hydrogen, Ka1 much greater than Ka2, which is much greater than Ka3. Carbonic acid, hydrosulfuric acid, both have 2 hydrogens. Ka1 greater than Ka2, greater than Ka2. Sample problem 18.10. Ascorbic acid, known as vitamin C, is a diprotic acid. Okay, that means you have 2 hydrogen. Ka1, Ka2 are both given, and this acid is found in citrus fruit. Calculate the acid concentration and the anions generated by the acid dissociation reaction and the pH of 0.05 molarity. Okay, so this concentration is the initial concentration. We want to calculate at equilibrium what is the concentration for the acid and the anions. Okay, so to do that, we know that this reaction will dissociate twice. We first need to write the dissociation reactions equations, 2 equations to generate hydronium ions. Now, since Ka1 is much greater than Ka2, okay, you can see here. So when we calculate the hydronium ion, we can omit the second one. Okay, just use the first Ka1, first reaction, dissociation reaction, to calculate hydronium ion. And during the reaction, during the calculation, as we did before, okay, we can make assumption that because Ka1 is very small, 10 to the minus 5, so we can neglect the change x during the calculation of x. Okay, so when we solve x, we'll see later. Okay, so we set up a reaction table for the first dissociation. So first dissociation with x equal to the dissociated acid. Okay, and then solve hydronium ion and the anions. So here are the 2 reactions. Okay, you start with the acid with 2 hydrogen. Okay, this after first dissociation, you get anion with 1 hydrogen, and then this 1 hydrogen dissociated again. Okay, give you anion with 2 hydronium ions. Okay, these are the Ka1 Ka2. To calculate the hydronium concentration, we only focus on the first dissociation reaction, and that is the ascorbic acid with 2 hydrogen react with water, forms anion with still 1 hydrogen and the hydronium ion. And so this reaction has a acid constant Ka1. Okay, so as usual, we write initial, which is 0.05 for the acid given, and change and equilibrium. Okay, so now to solve X, we use equation of Ka1. So Ka1 should be product divided by reactant, and product is X times X squared, and the reactant is 0.05 minus X. And as usual, we make the assumption that because Ka1 is a very small number, 10 to the minus 5, so X must be very small, can be neglected, okay, negligible, and therefore we have X squared divided by 0.05, which is the initial concentration. So we have the same equation to calculate hydronium ion, which is square root acid constant initial concentration. Okay, plug in the data, and the answer is 7.1 times 10 to the minus 4. So this is the concentration of hydronium ion that generated by the first dissociation reaction of the acid, weak acid. Now the second dissociation must also generate the sum, but because the Ka2 is so small that compared to this hydronium ion, this must be negligible. Okay, so we assume that the hydronium ion in the solution are mainly generated just by this one, okay, by first one. Okay, so therefore we can calculate the pH value, which is negative log hydronium ion, which is this one. Okay, and that gives you 3.14 or 15. After we calculate hydronium concentration, now we look at the question that also asks you the anion with 1 hydrogen and the anion with no hydrogen. Okay, so if you look at the equation, the product is the anion with 1 hydrogen, and that concentration should equal to X. So the answer for this one is same. So 7.1 times 10 to the minus 4 is the anion with 1 hydrogen. But what about the second one, the anion with no hydrogen? Now this one is generated by the anion with 1 hydrogen, so it gives you the anion in the second dissociation reaction, not the first one. In order to calculate concentration of this anion, we have to look at the second dissociation reaction. Here is the second dissociation reaction. This reaction starts with the anion with 1 hydrogen and give you anion with no hydrogen. Okay, and this is Ka2, which is the product divided by reactant. In this equation, the product or reactant is calculated from the previous slide. Hydronium also calculated from previous slides. In fact, these two are the same, so actually you cancel each other. And this is one you need to calculate. Okay, so from here we can calculate the anion with no hydrogen, cancel the 2 hydronium ion and the anion with 1 hydrogen, and that give you just the Ka2. Okay, so that's the answer for the anion with no hydrogen. Now at the last step, we need to check the assumptions, because during the calculation we assumed that the hydronium ion is only contributed by the first dissociation reaction. The second one contribute too small to be counted. So is this assumption valid? Okay, so let's see. So for the second reaction, So this reaction is a weak acid dissociation reaction. We use the same equation we derived before. If it's a very weak acid, the hydronium ion is calculated by acid constant times initial concentration. So initial concentration for the second dissociation reaction is the anion with one hydrogen, which is calculated from last slide. So you put in, you get 6 times 10 to the minus 8. And this is so small, it's even smaller than the hydronium ion generated from pure water. So the assumption is justified. Another assumption we made is the acid, dissociated acid, is so small compared to the initial concentration. We make assumption 0.05 minus x is approximately just the initial concentration, okay, because it's so small. All right, so to justify that, we use the calculated x, that's the x, or hydronium ion, divided by initial concentration. You get 1.4, which is much less than 5%. So assumption is justified. Non-metals and hydrogen forms hydride. For example, hydrogen bromide can be considered as a non-metal hydride. The acid strength of this non-metal hydride depends on electronegativity of this non-metal and the strength of this bond. Across a periodic table from left to right, electronegativity increase. As we all know, fluorine has the highest electronegativity. When electronegativity increases, the bond becomes more polarized. The non-metal becomes more negative charged. Hydrogen becomes more positive charged. And the proton can be easily pulled away from the bond, and the acid becomes a stronger acid. So across the period, acid strength increase. Down a group from fluorine to iodine, for example, atomic size increase. The bond length between hydrogen and the non-metal also increase. When the bond length increases, the bond becomes weaker, and the proton can easily come off, and therefore the acid becomes stronger. So down a group, acid strength increase. Here compares group 6, group 7 non-metal hydrides. From left to right, electronegativity increase. The acid becomes stronger. So hydrofluoric acid is a stronger acid than water. Hydrochloric acid is stronger than hydrogen sulfide. Down the group, the bond length increase, and the bond becomes weaker, so acid becomes stronger. So hydrochloric acid is stronger than hydrofluoric acid. Hydrobromic acid is stronger than hydrochloric acid. All oxo acids have the acidic hydrogen bonded to an oxygen atom. Here shows two examples. The first one is nitric acid, HNO3. This hydrogen is bonded to an oxygen atom. The second one is sulfuric acid, H2SO4, which is a diprotic acid. The two hydrogens are both bonded to the hydrogen atoms, or to the oxygen atoms. Now for oxo acids, the acid strength depends on the electronegativity of the central nonmetal and the number of oxygens. For oxo acids with different number of oxygen atoms, the acid strength increases with number of oxygen atoms. For example, you have learned before that when the number of oxygens minus number of hydrogen equals 2 or more, then they are strong acids. Okay, so the more oxygens, the stronger the acids. If they have the same number of oxygen, then the acidity or strength of acid depends on the electronegativity of the central nonmetal. Here shows two examples of the relative strengths of oxo acids. In A, we show three oxo acids. Okay, one is iodine bound to one oxygen and hydrogen. Second one is bromine added to bonds to oxygen and hydrogen. And the third one is chlorine adds to one oxygen and hydrogen. So these three oxo acids, they all contain one oxygen, same number of oxygen. So the acid strength is determined by the electronegativity of nonmetal. Since chlorine has the highest electronegativity, so the third one has the largest acid strength, and then bromine, okay, and then iodine. In B, we show two acids. Okay, one is chlorine bound to one oxygen, and the second one chlorine bonds to 4 oxygen. Okay, if they have different oxygen, the more oxygen you have, the stronger the acid. So this one, which is perchloric acid, is much stronger acid than hypochlorous acid. Some hydrated metal ions are able to transfer a proton to water molecule. These metal ions will form acidic solutions. For example, in aluminum nitrate, aluminum ion attracts 6 water molecules to form a aluminum water complex. Now in this complex, aluminum is a small but highly charged ion, aluminum 3+. Okay, and so this actually will be more stabilized by a negative charged ion instead of neutral water molecule. So what happens is one of the water molecule will break hydrogen-oxygen bond so that it forms a hydroxide. And so one of the water becomes a hydroxide. So now aluminum will be surrounded by 5 water with 1 hydroxide ion. What happens to this proton? Okay, this proton goes to another water molecule to form a hydronium ion, and this makes the solution acidic. So in general, a small and highly charged metal ion like aluminum will withdraw enough electron density from oxygen-hydrogen bonds of the bonded water molecules to release hydronium ion or hydrogen ion. With water becomes hydronium ion, and the solution is acidic. In this diagram, the left side shows the hydrated aluminum ion. Aluminum ion is in the center, which is surrounded by 6 water molecules. Each water molecule uses a lone pair electron of oxygen to bond to the aluminum ion. One of the water molecule, oxygen-hydrogen bond break, assisted by a neighboring water molecule to form a hydroxide, and the hydrogen bonds to water forms a hydronium ion. Just like weak acid ionizes in water, weak base also ionizes in water. Base accept the proton from water molecule to generate a conjugate acid, at the same time forms a hydroxide ion. Similar to Ka, the acid constant, the Kb is the base ionization constant, which is conjugate acid, okay, this one, multiplied by hydroxide formed, divided by the base concentration. This shows a base methylamine ionization reaction in water. So the nitrogen, here is the nitrogen of the amine, use a lone pair electron to approach a hydrogen of water molecule, form a bond here, and oxygen-hydrogen bond break, and this gives you the conjugate acid and also a hydroxide ion. This table shows Kb values for some molecular bases. Just like Ka, which measures the strength of acid, Kb also measures strength of the base. The larger the Kb, the stronger the base. The smaller the Kb, the weaker the base. Sample problem 18.11. Dimethylamine, a key intermediate in detergent manufacture, has a Kb this value. What is the pH value of 1.5 molarity of this base? Okay, so in order to calculate the pH, we must know hydronium ion concentration. Okay, that's the definition, negative log hydronium concentration. Now, if it's weak, if it's a strong acid, then this equals hydronium ion concentration. If it's a strong base, then this equals hydroxide concentration. And then from hydroxide concentration, we can calculate hydronium ion concentration. Now, if it's a weak acid, then we have to draw the reaction table, use Ka to find the hydronium concentration. Now, in this case, it's a weak base. So this is a weak base. All right. Just like weak acid, we need to draw the reaction table. Now, in the table, we'll use Kb to solve the hydroxide. Instead of hydronium, we solve hydroxide. And then from hydroxide, calculate hydronium ion concentration. All right. So remember, if either weak acid or weak base, we need to draw a reaction table. Okay. So the reaction for this base is the base plus water forms conjugate acid. Conjugate acid is when the base abstract one hydrogen from water to give you conjugate acid plus hydroxide. Okay, that's the reaction. All right, and then as usual, we draw initial concentration. All right, initial for base is 1.5, and change reactants is negative x, product is positive x, and equilibrium. Okay, so how do you solve x? Okay, we look at the question. The given is Kb, so we need to write Kb. Kb is the product divided by reactants. In this case, is the conjugate acid, which is x, hydroxide also x, so it's x squared divided by the base, which is 1.5 minus x. Now, as we did in the acid calculation, we make an assumption that this is a weak base. Okay, if we look at the Kb, it's a small number, and that indicates x may be very small, so we can omit x in this equation, so we get x squared divided by 1.5. All right, and now x can be easily solved. So x is the square root of Kb multiplied by 1.5. Now 1.5 is the initial base concentration. So the equation is Kb times initial base concentration. Now this equation reminds us the weak acid. So for weak acid, the equation to calculate hydronium is Ka times acid concentration. So here is the Kb base concentration. All right, so plug in and we'll get 3 times 10 to the minus 2 molarity. Okay, so before we go on to calculate the hydronium ion, let's justify our assumption that x can be negligible. So we use x divided by initial concentration, give you 2%, and so it's very, very small, and our assumption is justified. Okay, so next, how do you calculate pH value? We still need to calculate hydronium ion. We already have hydroxide, and we use the fact that hydroxide hydronium ion product is 10 to the minus 14. Okay, so hydronium concentration is calculated by Kw divided by hydroxide. Kw is 10 to the minus 14. Hydroxide is calculated from last slide, and that gives you 3.3 times 10 to the minus 13. pH value is negative log hydronium ion, which gives you 12.48, and this is greater than 7, and that is consistent with the fact that the solution is a weak base. Many weak acid and weak base are neutral molecules. Sometimes anions can also be weak acids or weak base. The anions of weak acids are often function as weak base. These anions will take a proton away from water to form a conjugate acid, at the same time generate hydroxide, make solution basic. Okay? So a solution of weak acid is acidic, but a solution of the anion of the weak acid is basic. Now let's use hydrogen fluoride as an example. When hydrogen fluoride is dissolved in water, hydrogen fluoride donates a hydrogen to water to form hydronium ion. At the same time, it gives the conjugate base. Now remember, in neutral water, hydronium ion equals hydroxide. So the water is neutral. Now, due to this reaction, when you add hydrogen fluoride, it generates some hydronium ion, and therefore hydronium ion now is greater than hydroxide. That makes solution acidic. Now, if we add the sodium fluoride salt in the solution, okay, in water, sodium fluoride completely dissolve, forms sodium ion and fluoride ion. The fluoride ion attract water molecules. It will take a proton, because it's a negative charge, take a proton away from water to form a conjugate acid. At the same time, water becomes hydroxide, and this make the water solution more hydroxide than hydronium ion due to this reaction, and therefore the solution becomes basic. Here again we show the weak acid dissociation reaction in water. So the weak acid add water forms hydronium ion plus the conjugate base, okay, or the anion. Now the anion in water also ionize. So this is the second one, is the conjugate base of the weak acid ionization reaction in water. Okay. Now if we combine these two reactions together, okay, so you will see the conjugate base cancel each other, acid also cancel each other. So the net reaction is 2 water forms a hydronium ion and a hydroxide ion. So you have learned already that if a reaction is the sum of 2 reactions, then the equilibrium constant, okay, this equilibrium constant for the total reaction is the product of the individual reactions. For the first reaction, K1 is a acid dissociation reaction. So this is the Ka of the weak acid. The second reaction is a anion take a proton away from water. So this reaction is the Kb. It's a base. So the anion serves as a base. So the equilibrium constant is Kb, and therefore we have Ka times Kb, that's these two, equals the K for the third reaction. Third reaction is water hydrolyzed to product to hydronium and hydroxide. So the K is actually the Kw. Okay, so we have Ka times Kb equals Kw. Now we can also prove by writing what is Ka, what is Kb, and you can see HA cancel, A cancel, and what you have is just the product of hydronium ion, hydroxide ion, and that is just the Kw. Okay, and so we have a important equation, and that is a weak acid acid constant multiplied by the conjugate base ionization constant equals Kw. This relation is true for any conjugate acid-base pair. So if we know one of them, we can calculate another one. Sample problem 1812. Sodium acetate, okay, which can be simplified as sodium acetate, has a concentration 0.25 molarity. And the question is, what is pH? Okay, so first we notice that sodium acetate is a salt of sodium ion, and the anion is acetate. Okay, if you look at the acetate, okay, this is CH3COO negative. That's the acetate. This comes from CH3COOH, which is organic acid. So the organic acid, a weak acid, forms acetate anion. As we already learned, the anion can serve as a base. So this salt is a base, okay? So, but it's a weak base. So in order to calculate pH, we need to know hydronium ion. To calculate hydronium ion, we need to know hydroxide because it's a weak base. So we need to draw a reaction table. Okay. Now in the reaction table, because it's a weak base, we need to know Kb. Okay. We'll see. We need the Kb. Now the question tells you Ka of this acid. So the acid Ka is given, and we want to know Kb of this anion or conjugate base. We just learned that Ka times Kb equals Kw. All right, so from this equation, we calculate the Kb, and then we use the reaction table to calculate hydroxide because it's a weak base. From hydroxide, then we calculate the hydronium ion, and then we calculate the pH. All right, so first we write the reaction of the base reaction. So the base reaction is the anion, which serves as a base. Okay, take a proton away from water to form conjugate acid plus hydroxide. All right, so that's the base reaction in water. So as usual, we draw initial concentration 0.25. That's the given for the salt. So the salt all becomes anion, okay, and sodium ion. So, but here we only need the anion, 0.25 molarity. Okay, the change, the equilibrium. Okay, so in order to use this table to solve X, we need to know Kb, and Kb is calculated by Kw divided by Ka. So plug in, we get Kb, and next we write the equation of Kb. So Kb is the product divided by reactants for this base reaction. In this table, it's X times X, so it's X squared divided by equilibrium base concentration, and again we assume X is very small, so it can be neglected, and so you get X squared divided by 0.25, and so Kb is given, and X can be solved by Kb times this initial concentration square root, and that gives you 1.2 times 10 to the minus 5 molarity, and this is the hydroxide concentration. Okay, so before we calculate hydronium ion and the pH value, first let's justify our assumption. So we use X divided by initial concentration, give you very small percentage error, and that is much less than 5, so assumption is justified. With the hydroxide concentration calculated, now we calculate the hydronium ion by Kw divided by hydroxide, and this is the result for hydronium concentration. So now we can calculate pH, which is negative log hydronium ion is 9.08. And again, this value is consistent with the fact that the acetate anion is a base. It's greater than 7. In previous slides, we showed that some salts, such as sodium acetate, well, anion comes from a weak acid, okay, acetic acid. This kind of salt is basic. Okay, in solution, water solution, they are bases. Okay, in this slide, we show that some salts are neutral in aqueous solution. A salt that consists of anion of strong acid and a cation of strong base yields a neutral solution. So here is an example, sodium nitrate. Okay, this salt, the cation sodium comes from a very strong base, sodium hydroxide. Anion comes from also a very strong acid. Okay, that's nitric acid. Okay, one comes from sodium hydroxide, one from nitric acid. Both are strong, and this kind of salt is neutral. Okay, in water, that's neutral salt. Okay, why is that? Well, first let's look at the sodium acetate. Now, sodium acetate has acetate anion that comes from a weak acid. Okay, because acid is weak, so there's a equilibrium between acetate and acetic acid. So if you have lots of acetate, it will combine water. Okay, go back to acetic acid plus hydroxide. Okay, because there's an equilibrium between these two. So the anion serves as a base to go back to the acid plus hydroxide, make solution basic. Now, if anion is a strong, comes from a strong base, for example, sodium hydroxide, it completely go to sodium ion, hydroxide ion, 100%. And that means there's no equilibrium. The hydroxide will not go back to sodium hydroxide. So sodium will not go back. So there's no equilibrium, okay, reverse reaction. And therefore, sodium does not, in other words, sodium does not react with water. Similarly, nitrate ion does not react with water because nitric acid completely give hydrogen ion and nitrate ion. There's no equilibrium. 100% go to the right side. It doesn't go back. So nitric acid does not react with water to have equilibrium with nitric acid. Okay, so this solution will be neutral because neither sodium ion nor nitrate ion will react with water to any great extent. So any salt, as long as the cation anion come from strong acid, strong base, the salt is neutral. A salt that consists of anion of a strong acid, cation of weak base, yield an acidic solution. So here is an example, ammonium chloride. The cation ammonium ion comes from a weak base, and that is ammonia. That's a weak base. Chloride comes from strong acid, hydrogen chloride. Okay, as we shown in the last slide, if this comes from a strong acid, there's no equilibrium between them. In other words, the chloride will not go back, to hydrogen chloride. There's no hydration reaction. Chloride won't react with water. On the other hand, ammonium comes from ammonia. There's an equilibrium. So if we have ammonium in solution, ammonium will react with water, go back to ammonia weak base, plus hydronium ion. Okay, so because of this reaction with water, it generates hydronium ion. This makes the solution acidic. Okay, due to the extra hydronium ion. Okay, now one way to remember this is that you look at the salt. Okay, one side is weak, so ammonium comes from weak base, but the chloride comes from a strong acid. Okay, so remember strong wings. So strong, okay, let's say strong wings. All right, so the right side is a acid, so it wins, and therefore the solution is acidic. Okay, acidic. So the salt has a strong acid. Okay, comes from strong acid, so the solution is acidic. But the real reason for the solution is acidic because the cation is come from weak base, so it go back. There's an equilibrium between this and the weak base, so it reacts with water to give back to the weak base. But water then becomes hydronium ion, and therefore the solution is acidic. A salt that consists of an anion of a weak acid and the cation of a strong base yields a basic solution. So we have already seen this. This one, sodium acetate. Sodium comes from a strong base, and acetic acetate comes from a weak acid, and the solution is basic. Okay, and this is because this comes from strong base. There's no equilibrium between base and the sodium ion, so sodium ion does not react with water. On the other hand, acetate reacts with water, and it abstracts the hydrogen from water to go back to the acid, and at the same time water becomes hydroxide. Solution is basic. So again, how do you remember that? Well, strong side win. So this is strong and this is weak. Okay, as acetate comes from weak acid, sodium comes from sodium hydroxide, strong base. So this wins. So base win, and therefore the solution is basic. Again, the real reason is the reaction with water of acetate, the anion reaction to give hydroxide. Sample problem 18.13. Predict whether aqueous solution of the following are acidic, basic, or neutral, and write an equation for the reaction of any ion with water. So to understand, okay, to predict whether a salt is acid or basic, we need to look at their ions. Okay, we need to first identify the cation and the anion, okay, and see whether they come from strong acid or strong base. Okay, if both are strong, then the salt is neutral. If one is strong, one is weak, for example, if cation is weak, anion is strong, then the salt is acidic. Okay, if anion is weak, cation is strong, the salt is basic. Let's look at A. Okay, A comes potassium perchlorate. Potassium comes from potassium hydroxide. That's a strong base. Perchlorate comes from perchloric acid, also strong. So both acid and base are strong. The salt must be neutral. Okay, so in A, the solution will be neutral. In B, the salt has a cation sodium, comes from sodium hydroxide, okay, which is strong base. And acetate, if you recognize COO, that is a anion come from weak acid, organic acid. So the acid should be CH5COOH. Okay, that's carboxylic acid. In fact, this is called benzoic acid. It forms benzoate anion. Okay, so the anion comes from a weak acid. Okay, as we showed before, the rule says stronger side wins. So this is strong base, strong base, weak acid. Solution should be basic. Okay, because the base is strong. Okay, acid is weak. All right, so the solution is basic. But the real reason is that because sodium comes from sodium hydroxide, it's strong base, there's no equilibrium, sodium does not react with water, go back to sodium hydroxide. On the other hand, the benzoate comes from a weak acid, so there's equilibrium between them. Okay, so benzoate react with water, go back to benzoic acid. At the same time, it generates hydroxide. So here is the reaction. Benzoate plus water, it takes hydrogen away from water to go back to the acid, at the same time generate hydroxide, and that makes the solution basic. So you can see that it's the weak side that react with water that cause either hydroxide or hydrogen to change. Okay, if both are strong, then neither of them react with water. So we should look at the side that is weak, that go back to its acid or base. Okay, next one, chromium nitrate. And nitrate comes from nitric acid. Okay, that's a very strong acid. So there's no reaction between them. In other words, nitrate will not react with water to go back to nitric acid. All right, so we need to look at the chromium. All right, now chromium is a small metal cation with fairly high charge density. As we shown before, this cation will be hydrated, and the hydrated ion will react with water to form a hydronium ion, and this is the reaction. Okay, it's hydrated with 6 water, and then one of the water becomes hydroxide. The proton goes to water, becomes hydronium ion, and that makes the solution acidic. What if both sides of a salt are weak? For example, ammonium cyanide. Ammonium comes from ammonia, which is a weak base. Cyanide comes from cyanic acid, which is a weak acid. So both sides are weak base, weak acid. So is this neutral, acidic, or basic? Well, it depends. Okay, because now both ions have a reaction with water to go back to their parent acid and base. Here are the two reactions. So ammonium, okay, go back to ammonia, all right, react with water to generate hydronium ion. So ammonium is a acid, okay, because it generates hydronium ion when it go back to the parent base. Cyanide, on the other hand, when it go back to the acid, it generates hydroxide, so it's a base. Okay, so in order to know if this salt is acid base, we need to look at the Ka and the Kb, okay, and see which one is stronger, which one is larger. Okay, if Ka is larger, that means ammonium is a stronger acid than cyanide as a base. Okay, so it has more ability to react with water, generate more hydronium ion. Okay, so we'll see their Ka, Kb. Here are two reactions, 1 and 2, and for 1, ammonium serves as an acid, so the Ka is shown here, which is 5.7 times 10 to the minus 10. And for the second reaction, cyanide serves as a base. So we look at the Kb, which gives you 1.6 times 10 to the minus 5. And because Kb is greater than Ka, that means cyanide is a stronger base than ammonium as an acid. So the solution will generate more hydroxide than hydronium ion, and therefore this solution is basic. One more thing about this slide is that usually Ka or Kb of a cation or anion are usually not given. So in that case, Ka for the cation can be calculated by Kw divided by Kb of the base, neutral base. So a neutral base Kb are usually known. Similarly, the Ka of this acid are usually known. So you use Kw divided by Ka, you give Kb of this anion, the conjugate base. Here we show some examples of salts and their acid-base behavior. So this salt, the cation come from strong base, anion strong acid. So these solutions are neutral. Okay, cations and anions, neither of them react with water. Okay, these salt, all right, cation come from weak base, anion come from strong acid. The solution is acidic. Okay, the real reason is the anion react with water, go back to the weak base, at the same time generate hydronium ion, make the solution acidic. Okay, now if anion is come from strong, just like here, strong base acid, the anion is a small, highly charged cation metal, then they can hydrate like this one. So it also give you solution acidic. In this salt, okay, the cation come from strong, okay, base. Anion is weak, come from weak acid. Note NO2 is not NO3. Okay, NO3, nitric acid is a very strong acid. HNO2 is a weak acid, and so NO2 will hydration, add water, go back to this weak acid, generate hydroxide, and so that makes solution basic. Okay, and it's helpful if you remember strong wings. So the strong side base wins. All right, but remember the real reason is the hydration reaction. It's the weak side react with water, go back to its acid, okay, generate hydroxide, make solution basic. Okay, now if both sides come from weak, all right, acid base, so this in this example, ammonium come from weak base. This is chloride, okay, come from chlorous acid. So this is weak, and this is also weak. They both react with water. In this case, you have to look at Ka, Kb, see which one is stronger, is the one which is higher. Sample problem 18.14. Determine whether aqueous solution of the following salts are acidic, basic, or neutral. To determine a salt is whether a acid, base, or neutral, we need to look at the ions, cation and anion. In A, we know the anion, we notice this is come from a weak organic acid. Okay, whenever you see COOH, that's organic carboxylic acid, you can have an R group. Okay, so in this case, I is just the H. So that's the weak acid, and this is the anion. Okay, when you deprotonate, you get this anion. Okay, so anion come from weak acid. Now so if it comes from weak acid, it will hydrolyze back. So there's a reaction, go back to this and generate hydroxide. Okay, we'll write the reaction. We need to write the reaction later. Now zinc is a metal that is similar to aluminum 3+. So zinc is 2+, a small, highly charged, and so it also hydrate and forms hydroxide, hydronium ion. So here are the two reactions. And the zinc, hydrated zinc, okay, pours hydroxide towards zinc. So you see the hydroxide, and the water, one hydrogen of this water goes to another water molecule, that will generate hydronium ion. So this reaction, you have seen this before for aluminum, right, and chromium. Okay, so you have seen this reaction. Now acetate, it comes from weak acid, so it go back to the weak acid by reacting with water, and so by abstracting one hydrogen from water, it gives you hydroxide. So the first reaction, zinc ion serves as an acid, so we look at the Ka, and in second reaction, the anion serves as a base, so it's a Kb. So we need to find the Ka and the Kb. Now we look at the textbook appendix. You should be able to find the Ka for the first reaction, zinc hydrate, Ka. Now for B, as we mentioned before, usually we know the neutral acid Ka, Kb. In this case, is the Ka of the acid. The anion Kb is not given, but we need to calculate. Kw divided by Ka, so this found from textbook, and that gives you this number. Okay, so compare with these two numbers, Kb, Ka. So Ka is greater than Kb, and that means the first reaction dominates. It generates more hydronium ion. The solution will be acidic. In B, the salt is a potassium hydrogen sulfite. The cation is potassium, which comes from potassium hydroxide. That is a very strong base. So potassium will not react with water. In other words, you don't need to consider potassium for the property, acid-base property for this salt. So we look at the anion. Anion is a hydrogen sulfite. Note that hydrogen sulfide has a proton, so it can deprotonate, okay, or dissociate the proton, forms SO3, 2 minus, plus a hydronium ion, which comes from this hydrogen. Okay, so that's one reaction, make it acidic. On the other hand, this can also go back to a diprotic acid, H2SO3. This is a weak acid. All right, remember H2SO4. This sulfuric acid is a very strong acid, but H2SO3 is a weak acid. So this will hydrolyze back to this one and generate hydroxide. So that will give you a basic. So one generate hydronium ion, one reaction, the other reaction generate hydroxide. So this anion can undergo two reactions, and we need to consider both and see which one dominate. Okay, so here are the two reactions, okay, detailed reactions. Hydrogen sulfide, okay, in water, it dissociate, give you the sulfite anion plus hydronium ion, okay, because this hydrogen goes to water. So that's a acid, okay, acid dissociation reaction. This anion also hydrolyze, okay, back to the sulfurous acid, okay. So by extracting one hydrogen from water and give you hydroxide, and that is a base dissociation reaction. So this anion is quite special. It can do both. Okay. So for the first one, we need to know the Ka. Okay. And for the second one, we need to know Kb. Okay. In fact, these two reactions are related by the diprotic acid H2SO3. This diprotic acid can hydrolyze. If you add water, it can go to first dissociate, forms hydrogen sulfide, okay, and plus, so it gives hydrogen, so hydronium ion, okay, so that's first dissociation reaction. The second one, it go to SO3, 2 minus, plus another hydronium. Of course, this will also add water. So this is a Ka1, this is a Ka2, okay? I hope you still remember for a diprotic acid, it can dissociate twice. And there are two acid constants, Ka1, Ka2. Now, in fact, this first reaction is the second dissociation reaction. Okay, so from textbook you can find Ka2, and that is this Ka. Okay, what about the second reaction? The second reaction is the opposite of the first one. Okay, the first one is a diprotic acid that goes to hydrogen sulfide, but this here is the diprotic hydrogen sulfide that goes to diprotic acid. So this is the opposite. In other words, this is Kb is Kw divided by Ka1. Okay, Ka1, Kab can both be found from textbook, and so here is Ka1. That's this one. Okay, this is a Kab. All right, Kab. So Kw divided by Kab, Ka2. Okay, Ka2 give you Kb. Okay, so now you have the first reaction acid constant, the second reaction base constant, and you can see acid constant is 10 to the minus 8, much greater than the base constant. That means the first reaction dominates, and so the solution is acidic. We have discussed two acid-base theories. In Arrhenius acid-base theory, acid is defined as a compound that can donate proton, and the base is a compound that can donate hydroxide. Okay, so as long as a compound has proton can donate, that's acid. And if a compound has a hydroxide, for example, sodium hydroxide, that's a base. And that is in Arrhenius acid-base theory. In Bronsted-Lurie theory, okay, we look at the reason why hydrogen proton hydroxide react is because the hydroxide has a lone pair electron that can react with the proton. In other words, it can accept proton. So in this case, we define acid is the same, but the base is anything that can accept proton. Okay, then it's a base. So this theory extends Arrhenius theory because now not only hydroxide can accept proton, ammonia can also accept proton because it has a lone pair electron, can react with proton. So that's the second theory. Now today we introduce a third theory. In this theory, we again look at the reason for the reaction is because of the lone pair electron. But this time we're not saying it's accept the proton, but we say anything that has a lone pair electron is a base. Anything can accept this lone pair electron because the proton, when proton react with this lone pair electron to form a bond, it's also saying that proton accept the lone pair electron. And so in this case, not only proton is a acid, but aluminum can be an acid too because it has it can accept lone pair electron. Okay, so in Lewis acid base theory, a Lewis base must have lone pair electrons, just like hydroxide has lone pair electron, ammonia has a lone pair electron. So these are called Lewis base. But of course, these are also Bronsted-Lurie base, and hydroxide is also Arrhenius base. Okay, what about acid? Acid is anything that can accept lone pair electron. Okay, so such as hydroxide or hydrogen, proton can accept that lone pair electron from hydroxide. Now, usually it must have a vacant orbital, because if you have an empty orbital, then it can accept lone pair electron. Okay, for example, proton doesn't have electron, so it can accept lone pair electron. Aluminum 3+ has 0 empty orbital, valence orbital, and therefore it can accept lone pair electron. Boron is another example that has 3 electrons but has a p orbital that is empty, and so it can accept a lone pair electron from ammonia, for example. And so boron is boron. So let's say borane. Okay, that's a Lewis acid too. Okay, not just proton, but borane is a Lewis acid. It can accept this lone pair electron. So in this theory, we focus on the lone pair electron. Okay, it has a lone pair electron, is a base. Accept lone pair electron is an acid. Okay, so Lewis definition expand the class of acid. Here again shows the reaction between boron trifluoride and ammonia. You can see in boron trifluoride, boron is group 3. Okay, is group 3 main group elements, means it has 3 valence electrons. So after forming 3 bonds, boron has no electron on its p orbital. So it has an empty p orbital. And when ammonia approaches boron trifluoride, the lone pair electron goes to the empty p orbital, forms a bond. So that's a new bond. So in this reaction, boron accepts lone pair electron. It's called Lewis acid. And ammonium provide lone pair electron, and it's a base in Lewis theory. And they forms a adduct. Here shows a reaction between sulfur dioxide and water molecule. In sulfur dioxide molecule, there are 2 double bonds. Both are sulfur and oxygen double bond. And because of this double bond, sulfur electron density are very low because electrons are pulled away towards oxygen. So sulfur becomes very positive. That means sulfur has electron deficient. And when water molecules approach sulfur dioxide, the lone pair electron of oxygen can approach the electron deficient sulfur central sulfur atom, forms a new bond. So this is the bond, oxygen-sulfur bond. So in this reaction, sulfur dioxide accept lone pair electron from oxygen, and it's considered as an acid. And water molecule provide lone pair electron, it's a base. Some metal cations can react with water molecules to form hydrated metal ions. For example, aluminum 3+, okay, ion. All right, these cations they have empty d orbital, and water has lone pair electron. So the water donate lone pair electron to the empty d orbital of this metal ions, and forms hydrated metal ion complex. So in this case is metal hexohydrate molecule. Okay, so in this reaction, water is considered a base. It provides lone pair electron, and the central metal ion accept lone pair electron. It's an acid. Sample problem 18.15. Identify the Lewis acids and Lewis base in the following reactions. To identify Lewis acid, Lewis base, we look at the formulas and to see which one accept electron pair, which is Lewis acid. If they donate electron pair, that's Lewis base. Okay, so let's look at the first reaction. Proton hydroxide. Proton doesn't have any electron. Hydroxide has a lone pair electron oxygen, so this oxygen goes to hydrogen proton to form a bond. And therefore, proton is an acid. Okay, so proton is a Lewis acid, and hydroxide is a Lewis base. Okay, look at the second one, B, and boron. We already talked about that because boron has an empty p orbital, and the chlorine, negative charged chlorine, has actually 4 pairs of electrons. So it donates 1 pair of electron to this empty p orbital, forms a bond. So chloride ion is a Lewis base. Okay, donate electron pair, and boron trichloride is a Lewis acid. Okay, last one, potassium plus. Okay, so a plus usually means it doesn't have electron, so it can accept lone pair electron. Water, oxygen has lone pair electron, donate to potassium, and therefore potassium is a Lewis acid. Water is a Lewis base.